Thank you very much for the kind invitation. And so, so I work in the quantronics group in the SPEC in CEA Saclay, and I'm going to present you our experiments on detecting spin fluorescence with a microwave photon counter. So the background of this of our work is really the field of electron spin resonance spectroscopy, whose aim is to take a sample and detect the presence and characterize also unpaired electron spins inside this substrate. And so the usual way that this is done is to put the sample in a magnet to polarize the spins and to probe them with microwave fields. So send some microwaves, drive some Larmor rotation of the spins, and then sense the microwave field, which is sent back by the spins. And so using this simple principle of inductive detection of the electron spin resonance, this is a very useful and widespread technique in many fields of science, chemistry, molecular biology, even food control, archaeology, and condensed matter physics. And so this principle and this technique is known for since the 50s, and it has a wide range of applications, as I said, but it is plagued by a very low sensitivity, meaning that you need a large number of electron spins to have sufficient signal-to-noise to detect some signal. And so the focus of the research in our group is to revisit electron spin resonance spectroscopy using techniques borrowed from the field of superconducting circuits. And this field includes a number of tools, and in fact, we're going to see in this talk each of them contributing in some place. Superconducting resonators, superconducting amplifiers, superconducting qubits, and with the help of these new tools that are provided by superconducting circuit research, is to revisit ESR spectroscopy in a regime where the interaction between the spin and the microwave field is going to be quantum, and in a much more nanoscale area with so small numbers of spins, and increase the sensitivity of spin detection. We will work at millikelvin temperatures, and one of our ultimate goals, which is not achieved yet, but we are very hopeful to reach it in the coming months, is to reach single spin sensing. So the outline of my talk is, so first I will describe how we are using these superconducting circuits to push a standard ESR spectroscopy to the quantum limit. And in particular, I will emphasize some novel effect that we have, novel with quote, effect that we have discovered in this process, which is the spin Purcell effect. And in the second part of the talk, I will describe a completely new method that we have developed in the recent year with my colleagues to perform ESR spectroscopy, but by measuring spin fluorescence and using a microwave photon counter. So, but first, I need to go a little more in details into the usual way to perform magnetic resonance spectroscopy. And so here we have our sample that contains the spins that we would like to discuss, to detect and to characterize. They are immersed in a magnetic field B0, and they are placed in a microwave resonator of frequency omega naught. And so we will apply the necessary B0 field so that the spin frequency, which is shown here as a solid line, matches the resonator frequency. And when they are in resonance, we are going to drive the cavity with some microwave field omega naught. And so we are going to detect the absorption of the microwave field by the spins, and so the interaction between the spins and the microwave field inside the cavity. And this interaction is described by a dipolar interaction between the magnetic dipole of each of the spins, or each of the n spins, and the B1 field of the resonator. Note that here I am writing the B1 field with, as an operator, and that is to emphasize that in our research we are going to aim at situations in which the quantum fluctuations of the magnetic field, of the B1 magnetic field, are going to play a role, which is not the case in usual ESR spectroscopy. And so this dipolar Hamiltonian can be written in the Jaynes-Cummings form between the Pauli and the operator and the field creation annihilation operators in the resonator. And here we see that the strength of this coupling between the spins and the field is described by the so-called spin photon coupling constant, which is the product of the B1 field vacuum fluctuations and the magnetic moment of the spin, which is the transverse operator between the spin up and down states, multiplied by the garomagnetic ratio. And this is obviously, and this is the case in all cavity and circuit QED experiments, this is obviously very important parameters in our experiment, and one of our obsessions is to increase it as much as possible. All right. So this is the principle, but now in practice, how does usual an experiment work to detect the spins? So the most usual detection sequence, spin detection sequence, is the Hahn echo. So we have our spins in the resonator, and they are described by the Bloch sphere. And so the Hahn echo sequence consists of applying a first pi/2 pulse to the spins, which rotates them on the y-axis of the Bloch sphere. And after this pi/2, what happens is that we have an ensemble of spins. They all have slightly different Larmor frequency, and therefore in the rotating frame, they will diffuse in the equatorial plane, and so the macroscopic magnetization along the y-axis is going to be lost very rapidly because of inhomogeneous broadening, right? And this is lost and then we can wait for some time tau. But then this diffusion due to inhomogeneous broadening, to static inhomogeneous broadening, can be counteracted by the action of a pi pulse. And this pi pulse leads effectively to a refocusing of the spins. And so after a 2 tau after the first pi/2 pulse, all the dipoles, all the magnetic dipoles are going to go back in phase along axis y. This will give rise to a macroscopic magnetization, macroscopic oscillating dipole that will then lead to the emission of a pulse, of a microwave pulse. This pulse is called the spin echo. And basically, magnetic resonance wants to detect as well as possible this echo, and this is a bit the focus of our experiments. And so now this echo, so we have to really look how is this microwave pulse detected, this weak microwave pulse, and in usual setups, the microwave echo is amplified, and then it's demodulated by mixing with some local oscillator. And then we can obtain the 2 quadratures of the field, and the echo will be contained in one of the 2 quadratures because it has phase coherence with the driving pulse, right? So it is the echo is a phase coherent signal, and therefore appears on one of the 2 quadratures of the field. All right. So we are going to be again obsessed with having maybe the strongest echo and the less noise, right? This is really a very practical question of sensitivity. Sensitivity is just a question of signal to noise. And therefore, we are going to look a bit in detail what is the amplitude of this spin echo. And the amplitude can be written simply. These are dimensionless units of the field. And so the first factor in this expression is the equilibrium spin polarization. Right? So this is the difference of spin up and spin down divided by the total number of spins. And this is, yes, this reflects the fact that we cannot, in this process, we cannot have more, that spins that are thermally excited will not contribute to the signal, and we are only sensitive to the difference in spin up and spin down. So we have this spin polarization, this equilibrium spin polarization. The echo amplitude is proportional to the number of spins. Note that this is the amplitude of the field, and this comes from the fact that the echo emission is a coherent phenomenon. Each spin is radiating some signal, and it's really the sum of these fields which interferes and which produces this echo. Therefore, the amplitude of the spin echo is proportional to the number of spins. Then we have this coupling constant, G, which is not so surprising. This is really indicating that the more strongly one spin. Here I consider that all the spins have the same coupling. This is an easier situation. And then we have here the echo duration. This is a parameter that is related to actually the inhomogeneous broadening of the spin ensemble. And kappa is the damping rate of the resonator field, and so it's related to its quality factor. It's the damping rate of the energy inside the resonator. So this is the spin echo amplitude, but of course we have to be concerned with the noise. And here again, this is a very practical question. So the noise, we can write it as the square root of a number of noise photons, let's say, and this number of noise photons has really two origins. One is the equilibrium noise that is present at the sample, and this is really, in a sense, the thermal noise that is present in the line, the Johnson-Nyquist noise. But that is not all there is. There is also a contribution of the amplifier. So we have also to take care of how good is the amplifier, because really we are concerned with practical questions of signal to noise at the output of the cryostat and really of the spectrometer. All right, and so what I want to show you in the next slides is that superconducting circuits are actually offer very good ways to both increase this signal and decrease the noise, and that's the goal for increased sensitivity. So first thing is, so here I write again this signal to noise ratio, and first thing is that we have interesting devices with superconducting circuits that are these micro resonators. So what we use, we have some substrate that will in fact contain our spins close to the surface, and on top of this surface you see that we can pattern a superconducting thin film resonator that consists of some capacitor. You see, this is you have to imagine this is a superconducting thin film, which is a few tens of nanometers thick, and you see it's just a capacitor which is shunted by some wire. And so this is an LC resonator, a lumped LC resonator. It's hard to do simpler. But what is interesting with the fact that it's superconducting is that we can have very low levels of dissipation and still use very narrow wires. So here you see this is a zoom of the wire. This is the inductance. And you see that basically we can bring this wire as narrow as a few hundreds of nanometers. So in practice, we will vary between 100 nanometers and 10 microns. These are typical numbers. But this means that the B1 field is going to be very confined around this electrode, and therefore that this will also lead to an enhanced coupling constant. And so with this kind of geometry, we have spin photon coupling constants that are still not spectacular in the 10 to 1 kilohertz, 10 hertz to 1 kilohertz. This is not enormous, but this is many, many orders of magnitude higher than in usual electron spin resonance spectroscopy, where the coupling constants are more on the millihertz level. All right, so that's good for the signal. Again, we increase G. Now, also, superconductivity enables to have a high quality factor for the resonator. This is a resonance that we measured, I think, at 7 gigahertz, and you see that it can be 20 kilohertz wide, corresponding to quality factors that can go up to 1 million typically. And so, again, this is good for the signal because now we are reducing kappa, the loss rate. Right? Note that we are still in the limit where G is smaller than kappa. So this is, for the experts in the room, this is the bad cavity limit. We are not in the strong coupling regime of one spin coupled to one resonator. We are still in this bad cavity limit. But nevertheless, the quantum fluctuations of the field still have a very strong effect, and this is what we are going to see. So superconductivity, so let's not forget that we have to apply some magnetic field to the spins. And so this introduces a number of constraints because, of course, superconducting films do not like magnetic fields. So the first constraint is that B naught should be parallel to the substrate. There is no way out if we want to do things properly. And B naught cannot be too high. Too high still means that we can apply fields if we use the proper material, niobium or niobium alloys, we can still go to 1 Tesla without losing in the quality factor. We can still keep quality factors up to a few hundred thousands in a field of 1 Tesla. So this is still quite acceptable, and there is a wide range of parameters that we can do experiments in. Right. So another feature of our experiments is that they are performed at low temperatures. And in fact, we always work in the regime where kT is much smaller than h bar omega naught. And so, for instance, typical parameters for us are 7 gigahertz and 10 millikelvin. And so this is good for spin polarization because in this limit, spins are fully polarized. And this is also good for noise, for the equilibrium noise. Remember that in this expression we have this equilibrium noise that we want to minimize. And this equilibrium noise is the fluctuations of the microwave field. So this is the variance of the microwave field fluctuations. This is at high temperature, this is proportional to T. But remember that at low temperature there is a saturation. And in fact, this microwave noise saturates at a value which is which is a quarter, and this is the quantum limit. So in this regime of low temperatures, the field is essentially in its ground state, but we are left with field fluctuations. These are the well-known quantum fluctuations of the field. This is not a discovery, but this will be essential in these experiments. And so this is the so-called quantum limit. So thermal noise is suppressed, however, quantum fluctuations remain. All right, but so in a sense, this is kind of the best that we can do on the noise, but this is not enough. We also need an excellent amplifier. Otherwise, this effort of going to low temperature is useless. And so good amplifiers are also enabled by superconducting circuits. And these are relatively new developments. They have now been developed 10 years ago, I would say, that this is a field in itself, and these good superconducting amplifiers are, in fact, also realized with Josephson junctions, and they are called Josephson parametric amplifiers. And here is an example. There are many superconducting Josephson parametric amplifier designs. This is a selection of references, but the field it is a field of research in its own. And so this is the one that we have used in some of the experiments that I will describe, and so I will spend a few minutes describing it. And so this parametric amplifier, it consists, this is the core of the device. You see that it is again some LC circuits, but combined with an array of squids. And so there is an input port, which is just a capacitor. And you see that the input signal is sent, and the reflected signal is the output signal. So this is an image of the device. And so how does it work? So squids behave as a tunable inductor. A squid is a Josephson inductance whose value depends on the magnetic flux that is applied to each of the loops. And so this flux can be controlled if we have some nearby antenna. So you see, this is an image of the device. The squid array is here. And here we have this little antenna by which we can send currents. All this is superconducting, of course. And the current will generate a flux. And so we can tune this value of this inductance. And in this way, we can tune the the frequency of this resonator, right? So we will tune it between 6 and 8 gigahertz, for instance. But that is not all. So we can, in this way, we can choose some working point. But once we use this working point, we still need to power the amplifier. This is still some passive LC resonator, so there will be no gain. So the way to achieve gain is to provide energy, power supply, in the form of a microwave pump tone that will also be applied via the flux. And so if we modulate the flux in each of the loops at twice the LC resonator frequency, then we will achieve some parametric gain. And so we have this strong pump tone that is sent on this antenna. This is the power supply. And because of this power supply, the input field will acquire a higher amplitude in the reflected, will be reflected with a higher amplitude. Right? This is the principle of this parametric amplifier. And so this is a gain curve. Now, of course, we need to prove that it works. This is a gain curve proving that we can achieve more than 20 dB gain. This is with respect to half the pump frequency. And so you see the bandwidth is not enormous, but the gain is sufficient. So since we are working with very narrow band signal, this is not such a big problem. And so an interesting feature of these parametric amplifiers is that in fact, they are quantum limited in the sense that they do not add more noise to the signal than is needed by quantum mechanics. And what is needed by quantum mechanics is expressed by Cave's theorem. And for just a normal amplifier, an amplifier that amplifies both quadratures equally, that has just one gain, then this limit is that the amplifier has to add a quarter of a photon to the signal. And this is a very fundamental limit. So then in this formula, we would have a quarter for the input noise, the vacuum noise, and another quarter due to the amplifier. But there is actually another mode of operation of these amplifiers, which is the degenerate mode. And this mode is implemented by using a pump tone on the amplifier, which is exactly twice the signal frequency. If we do so, the gain becomes phase dependent. And we have a well-defined phase between the signal and the pump, because there is just this factor 2 of difference between the two frequencies. And so we can change the phase, and you see that the gain now can reach, again, 20 up to 23 dB. But then if we change the phase of the input signal or of the pump by pi over 2, we will have full attenuation of the signal. And in this mode, this is the so-called degenerate mode of parametric amplification. And in this mode, the amplifier is actually noiseless. It does not add any noise to the incoming signal. And so n amp can be taken to 0. This is the analogous in optics of homodyne detection. Right? So we are amplifying one quadrature. We are measuring without added noise one of the two quadratures. So this is, So of course, these JPAs, they are not perfect. They have constraints. In particular, they have a very low dynamic range. And you have to imagine that they will saturate typically at 1 picowatt input power. Right? So, and limited bandwidth, but now there are many new designs and many progress in the field that I will not describe, but typical modern state-of-the-art bandwidth can reach a gigahertz. All right, so combining all this together, all the experiments that I'm going to describe, they are done in some dilution cryostat. This is a photograph of a cryostat in our laboratory. All this is at 10 millikelvin. You have to realize these are like large volumes and weights of copper. And so at this cold stage, at 10 milliK, we have here some coil, in fact, double coil that is homemade, and we install the sample inside the coil with the spins and the resonator, this type of samples. And then they are probed by measurement lines. So you see they have many coax lines. And in particular, so the reflected signal is going to this Josephson parametric amplifier, which is sitting here in this photograph. And then we have the rest of the wiring, which consists of a lot of attenuation at low temperatures in the input line, so that we use typical driving pulse powers of a picowatt to drive the spins. And then the reflected signal, together with the spin signal, is amplified by the Josephson parametric amplifier, which is powered by a pump line, and then is output here. And these are typical signals that we measure. You see here a Haneko sequence. We have two drive pulses, pi over 2 and pi. And then here, this is not the result of a drive pulse. This is really the echo from the spins. So this is a typical signal. And all the physics is by integrating this echo, and this is our measured quantity. So something I didn't mention so far is how fast can we repeat? We are really dealing with practical measurements. We want to measure interesting samples, and so we should be able also to repeat sufficiently fast to average the signal. And this quantity is related to a phenomenon which is spin relaxation. The reasoning is the following. After a spin echo sequence, imagine that in this, so now this is the time, and maybe I want to repeat my same experiment many times in order to get a lot of signal. And so in this little box, I have a spin echo sequence, but then at the end of the spin echo sequence, the spins are somewhere on the equator of the Bloch sphere. So they are not back to the, so in order to repeat, we have to wait that they go back to the ground state. And this occurs by energy exchange between each spin and some bath. So the spins need to lose energy, need to thermalize to their ground state to deliver their energy to their environment. This occurs in a time which is called the spin relaxation time, which is called T1. And so this is the minimum time that is needed for repetition. Now, there is a well-known problem in magnetic resonance that low temperatures are often associated with long T1s. And this is an example that is taken for donors in silicon, phosphorus donors in silicon. You see that going from 14 Kelvin, so if so the T1 time is in maybe the tens of microseconds at 13 Kelvin, but if we go down to 2 Kelvin, the T1 time goes up to 1,000 seconds or even higher. So this means that this is the minimum time you have to wait between each echo experiment. So this is a major issue. In fact, it prevents ESR spectroscopy at ultra-low temperatures. And so in our experiments, it turns out that we have a novel spin relaxation channel which enables us to overcome this problem. And here is the explanation. So again, as I said, we have the spin between these two levels, and spin relaxation occurs by energy exchange with its environment. And this energy exchange, so we are in the chair of atoms and radiation, so maybe the most natural, the first thing we would think of is radiation of a photon in free space. However, it is well known, and this is the same in atomic physics, that for a magnetic moment is a weak transition. We are speaking of microwave frequencies in the few gigahertz range, and so the relaxation by spontaneous emission in free space of a spin at 7 gigahertz takes 10,000 years. So spontaneous emission in free space is not relevant for spin relaxation. Therefore, spin relaxation in usual conditions takes place by exchange between the spin and the phonon degree of freedom, or by interaction with other spins. These are the relevant relaxation mechanisms. Now, this is not exactly the case because Purcell in 1946 predicted that, spontaneous emission can be strongly enhanced if these spins are enclosed in some cavity, in a resonant mode, and if they are, and there is the confinement of the mode, both spectrally and spatially, actually leads to an enhanced spontaneous emission of the spins at a rate which is the Purcell rate, and which at resonance, so omega s is the spin frequency, omega naught is the resonator frequency, so the effect is obviously strongest when the spins and the resonator are resonant, in which case this term is 1, and then the resonant Purcell relaxation rate is 4g squared over kappa. So here again we find our spin photon coupling constant, and we see that if we want this rate to be large so that T1 is short, we need a large G and a low kappa. And this is exactly the situation in which we are in our experiments. This is because these superconducting microresonators are very confined and they have a high Q. And this regime of Purcell relaxation has been reached for electrical dipole systems since the 1980s, with, in particular, maybe the first observation by Philippe Gouet et al. With Rydberg atoms, but since then in other systems. This is essential because, indeed, it allows to shorten T1 on demand and to accelerate spin thermalization. And so in our experiment, we can measure T1 of the spins. For that, we do so-called inversion recovery sequence. So we have this Haneko sequence, and we have, before the Haneko sequence, a first pi pulse, and we just wait between the pi pulse and the Haneko detection, and we see some exponential damping, and this enables us to fit T1. And this is the result when we plot. So this was measured for donors in silicon. And so now when we measure T1 as a function of the detuning between the spins and the resonator, we see that when the two systems are very detuned, the T1 is very long, is a few thousands of seconds, as measured for phosphorus donors. But on resonance, the T1 is drastically reduced to a level of 1 second. And this level of 1 second means that really the ratio between radiative and non-radiative relaxation at this stage is very high. So all the spins relax by emitting the photons, to essential. So these were observations in 2016, and in fact, they were the first observation of the Purcell effect for spins, which is a bit interesting historically because this was predicted for spins. Of course, Purcell was thinking of magnetic resonance. It was observed for other systems first, but and so it's also interesting because indeed we see an impact of quantum microwave field fluctuations on spin dynamics, which is say the entry door to cavity quantum electrodynamics phenomena. And very practically, this shortening of T1 time means that it is possible to perform ESR spectroscopy at millikelvin temperatures. And this is really because of Purcell relaxation. So now, what spin systems are we interested in our lab? So these are really basic principles. They can be applied to any spins, of course. Now, we have model systems that we like. So we work with NV centers in diamond, rare science doped crystals, and donors in silicon. And I will talk only of these two systems. But I also want to mention that we would be very interested also in doing more molecular measurements by depositing some molecules on top of these resonators or studying two-dimensional van der Waals materials. So this is a very rich field of research. So as an example of a real experiment, and so can we really benefit of this high sensitivity that we should have achieved? So I want to show a few measurements done on a system which is an erbium-doped crystal at 10 millikelvin. And so this crystal is calcium tungstate. So here is the crystalline unit. So calcium tungstate. So erbium substitutes for calcium ions. There is charge compensation because the charges are not absolutely correct, but let's forget about this. And erbium is paramagnetic. So erbium ions, in this trivalent state, is paramagnetic. And the interesting, so erbium-doped calcium tungstate is a model system for rare science doped crystal, and it has been studied since the 60s. What is interesting in our setup is that because of the very high sensitivity, we are able to probe calcium tungstate erbium dopings at ultra-low concentrations that are otherwise very hard or maybe impossible to measure with standard EPR spectroscopy. So in fact, we use a crystal that has not been doped with erbium, and we only rely on the residual traces of erbium, and we can see that we have 1 ppb of erbium, which is 10 to the 13 per centimeter cube, and which is much lower than the lowest concentrations that have been measured in this type of systems. And so, well, this is just an example to see that we can do spectroscopy. We can measure the erbium line, which is quite narrow, but the most interesting is the coherence time on this erbium line. And here to measure this coherence time, we can again apply a Haneko sequence, and then we vary the distance, the duration between the pi/2 and pi pulse, and this 2 tau delay. This is the delay between the first pulse and the echo. And how long this echo survives is the measure of the coherence time. And so we see that the echo, in fact, survives up to 20 milliseconds. And this value is quite remarkable. In fact, it's the longest electron spin coherence time measured in any natural abundance material. So there are materials that can be purified with low nuclear spins, because here we also have very clear evidence that this is actually limited by the spectral diffusion due to the nuclear spins in the crystal, in particular the nuclear spins of the tungsten atoms. And so we are very happy of this result, and we are investigating also possible applications in quantum information processing. Another example of system of interest is bismuth donors in silicon. And so here the physics is as follows. So we have our silicon lattice, and then one atom of silicon is replaced by a group 5 element. So it can be phosphorus, but we like bismuth, but the physics is the same because it has 5 valence electrons. So it will make 4 covalent bonds with the silicon lattice and give an electron to the conduction band at room temperature. But at low temperature, below 10 Kelvin, this electron can be trapped again on the potential given by the bismuth ion. And then we have this unpaired electron in the silicon crystal, which is attached to the bismuth. So this is, again, an unpaired electron. And this is donors in silicon are a model for ESR spectroscopy. And so I spoke of this electron spin. Now this is the energy level of these systems. You see here, you see that there are many energy levels. This is because the bismuth nuclear spin bismuth also has a nuclear spin. It's actually a 9½ nuclear spin, and therefore there are 20 energy levels. So this energy level is quite rich, let's say. And here are the allowed transitions between all these levels. And I don't want to speak too much about this, but I just want to emphasize that there are interesting points at which, in fact, some of these transitions are stationary in magnetic field. This is reminiscent in atomic physics of so-called clock transitions because they are used, because they are not sensitive to magnetic field, therefore they are good for metrology. And so here the same is also present in bismuth, and long coherence times are expected in this system. And in fact, so this is an example again of measurements of spectroscopy of these bismuth donors in silicon, measured again by the Haneko. So we have a Haneko, and we plot here the integral of the echo as a function of the B0 field. And we see many peaks. So the peaks correspond to some transitions. So we have a resonator that is here, and we are increasing the magnetic field. So we are crossing several transitions. So the peaks, these are the data, the open circles, and the blue line is the theory. In fact, the peaks are broadened and they are distorted. And this is actually very interesting. This is due to strain in the substrate. And we understand it quantitatively. But I don't want to talk about this. So this is for the spectroscopy. And we have also been able to measure the coherence time at one of these clock transitions, this one in particular at 27 millitesla. And here we find a coherence time of 300 milliseconds. Here I have to say this is also in isotopically enriched silicon. So we have used silicon where we have removed nuclear spins that are given by the silicon-29 isotope. And so this is also a very pure crystal. But these are very long coherence times that can be extended by using several pi pulses, using dynamical decoupling. And we are also interested in potential applications in microwave quantum memories. All right, but coming back to maybe this question of sensitivity, so now that we've seen practical examples, I would like to come back to this question of sensitivity. And so it's possible to actually plot these, a graph with signals. So all magnetic resonance experiments can be put in this form where we have this signal that is given by one echo and the noise in the y-axis. And then, depending on the level of signal, and we can have a minimum number of spins that can be detected with signal-to-noise ratio of 1 in one echo. Right? So we have kind of ISO lines of a minimal number of spins. And so it's interesting to see a bit. So a commercial ESR spectrometer is here, right? The noise, this is maybe room temperature, so 1,000 noise photons, a very low coupling, so this signal is very small. So commercial ESR is here. Then the state of the art in 2014 was here. These were like kind of standard low temperature measurements. And our experiments are here, so our and our colleagues. So there is this new generation of ESR spectroscopy experiments, which really goes in the range that the minimum number of spins detectable in one echo is in the order of 100. And so overall, we have improved the sensitivity compared to the state of the art by 10 to the 5 using these superconducting circuits. Of course, even much more if we compare to the commercial spectrometers. But yes, so this is all very nice. But in fact, so now we can always be willing to go further, right? And so it's an interesting question is. Can we go further, indeed? And in particular, there is this quantum limit of noise, which is a bit annoying. And it's a legitimate question is, can we go below this quantum limit? And here the idea is, well, quantum noise is limiting us, so maybe we can use squeezing, quantum squeezing, to reduce the quantum fluctuations in one quadrature. And here, because indeed, this is what limits us, right? So quantum squeezing, there is a long history, of course, of measurements beyond the quantum limit using squeezing, most of it in the optical domain, but also in the microwave domain recently, and I think this is not even up to date. So here what I want to discuss is an experiment where we show that squeezing can also be used to enhance magnetic resonance detection. And so the idea is very simple. So we have our spin system in the cavity, and we want to detect this spin echo. The problem is quantum fluctuations in the spin echo quadrature. Let's try to send on the sample some microwave squeezed state with the squeezing axis chosen appropriately so that the echo signal quadrature is squeezed. Then the echo will just be some displacement of this squeezed state, and therefore we should have reduced noise on the echo quadrature at the expense of enhanced noise on the other, but we don't care because the echo is just on one quadrature, right? So this is the idea of the experiment. And so how to actually make this squeezing? Well, this is well known by now. In fact, it's again using a Josephson parametric amplifier. In fact, the same as I already described to you can be used to generate a squeezed state. We just have to operate this Josephson parametric amplifier in the degenerate mode and without any input, right? So at the input, no input actually means that we have vacuum at the input. Vacuum then is amplified in a phase differential way. So one quadrature is going to be amplified at the expense of the other, and therefore this will take the form of a squeezed state. There will be less noise on this quadrature. So this is what we've done. This means that we have now two parametric amplifiers, one for detection and one for squeezing, actually. And so this, without entering too much into the details, squeezing, when you speak of squeezing, you have to show a curve where some noise is reduced as a function of some phase, right? And this is what is shown here. So this is, here let's forget about the spins. We are just showing that the squeezing works, right? And so this is the total noise at the output as a function of the phase between the squeezer and the detection amplifier. And we see that the variance for most of the phases, the noise is higher, but there is this little region where the noise is actually reduced by turning on the squeezer. And this is, so without squeezer, we would have the blue, the variance is the blue line, and we reduce it. And this is now the histogram showing that Gaussian distribution of field. This is a histogram of measuring the field many times and plotting the results and making a Gaussian histogram. And we see that this is the blue curve is the curve when the squeezer is off, and when we turn on the squeezer, we see that we obtain the red curve, which shows that there is a little bit of less noise. It's not very spectacular. But so this is not new. This has already been observed. Microwave squeezing is not new in itself. What is new is that we can now apply it to spin echo detection. So we can combine this squeezing with spin echo. And to do that, we actually use our spin echo sequence. And during the echo emission only, we pulse the squeezing, we turn on the squeezing. And this is what we obtain. So these are, we can compare the echo squeezing on and squeezing off. And when we take many curves, and when we average, we find exactly the same echo. This is actually good. It means that the amplitude of the echo is the same. But the noise is reduced. So this is, there is a little bit less noise in the red curve than in the blue curve. It's not spectacular. You see that the noise reduction is 20% in variance. So this means that we gain in sensitivity by 12%. So it's not super practical. We know exactly what is limiting us in this experiment, and we could probably do a bit better nowadays. So it's a nice proof of concept that indeed squeezing can be used for enhancing magnetic resonance spectral sensitivity, but it's still a little bit disappointing, and honestly, we would like to do much better. So is there a way to do much better? And this is now the second part of my talk, where I want to introduce this new method that we are very interested in and very excited about, which is incoherent detection of spins. So again, this is now again a sketch of the experiments that we do. We have our little spin echo sequences that are maybe they don't last very much. It's maybe 100 microseconds, and then we have these long waiting times T1 for the spins to relax, and then we repeat our echo. Right? And so the echo detection, again, the signal-to-noise ratio is given by this formula that I described at the beginning. Here I take the polarization to be 1 because it's just simpler. And again, the problem here is that the signal-to-noise ratio is limited because in the n, in the noise, we have the fact that n is larger than a half, and that's due to vacuum fluctuations of the microwave field. So that's kind of a hard bound. So what can we do really differently? Well, the idea would be, let's maybe not measure the field, but measure the energy operator, because, of course, energy, vacuum is an eigenstate of the energy, so the vacuum state is evidently noiseless when it's detected by an energy detector. And so we would like to use then a photon counter to detect the spin signal. And moreover, but if we do that, we can also do something that is quite interesting, because we are not limited to detecting the echo. We can also detect all the photons that are emitted during spin relaxation. Let's not forget that spin relaxation in our experiments is nearly entirely radiative. So during this T1 time, the spins are relaxing by emitting many incoherent photons that are not used for detection. It's a little bit of a waste. And so we would like to detect this incoherent emission during spin relaxation in the Purcell regime. And if you think about it, this is actually quite nice, because if you have an ideal photon counter, it is absolutely obvious that there is no limit on signal to noise that you can achieve. Indeed, the spins, as I said in our experiment, relax entirely radiatively. So n spins will emit n photons. So if you have an ideal photon counter, you can detect them all, and there is no lower bound or upper bound in the physics of this detection mechanism. Of course, there are non-idealities, and we are going to see them, but in principle, this method has infinite signal-to-noise ratio, infinite sensitivity. All right, so okay, so first thing that I would like to say is that spin fluorescence has already been detected by some experiments in the 80s, and this is the first. So this experiment was the first detection of spin fluorescence, but that was in a quite different setup. So I just want to describe this experiment. So here again, they had this ensemble of, in their case, they were nuclear spins, in fact, in some LC resonator. So it was a large ensemble, maybe 10 to the 23, like a molar number of nuclear spins, so maybe 10 to the 23 nuclear spins. And again, this is connected to some measurement line, amplifier, and mixing with a local oscillator. And what they did is they apply some saturating pulse to the nuclear spins, and then they just measure the output power. And this is what they see. So you see that you have here some noise curve. This is due to thermal noise and various noise. This is the noise response essentially of the LC resonator. And then there is a tiny bump here. And this tiny bump is actually the spontaneous emission of the nuclear spins at 30 megahertz. So, and this was also confirmed in many experiments, etc. So this is very nice. But you see that we have 10 to the 23 nuclear spins, and all we can get is this tiny bump. So it doesn't sound like a very, it's not necessarily very promising in terms of sensitivity. And in fact, I think the interest of this method for really detection purpose is only there if you have a photon counter. Because you see that here, the problem is that without the spin emission, there is the spin emission is on top of a very, very large background. So it's just a tiny bump in emitted power. And you need to be in the photon counting regime, like in optics. For doing fluorescence detection, you need a photon counter. All right, so, but there is a problem. I mean, microwave photon, so this is the experiments that we would like to do. We have our spins, our resonator, and then we would like to just collect the fluorescence and send it to a single microwave photon detector. Now, the problem is that they don't exist. I mean, they don't exist commercially. But the good news is that their operational microwave, single microwave photon detectors are a subject of active research, and they have been developed in the very recent years using superconducting qubits. And this is a list of references. Here I want to focus on the work that actually was performed at the ENS by Emmanuel Furin and Zaki Lektas and Raphaël Descanes, published last year. And this is their design that, together with Emmanuel Furin, we have used for our experiment. And so I'm going to describe the principle of this photon detector now. But first, I have to explain to you very quickly what is a Transmont qubit, because this is the building block of the single microwave photon detector. And the starting point is, again, an LC circuit. An LC circuit has energy levels that are equidistant. NC is the LC circuit frequency. And therefore, this is not a two-level system because the levels are equidistant. So the idea of the Transmont qubit is to replace the inductance by a Josephson junction. A Josephson junction is a very strongly nonlinear inductor. And in fact, it is so nonlinear that the nonlinearity will be felt as early as the second energy excited state of the circuit. And therefore, a Transmont qubit is a resonator, is a microwave resonator made anharmonic at the single photon level. And so then in this way, we have isolated a two-level system, because if we excite it on resonance, there is no other level that it can go to, so it is anharmonic. this is a picture of a junction. A junction is, again, a tunnel junction between two superconducting electrodes. And so this is the principle of all, I mean, many superconducting qubits used nowadays. This is the so-called transmont qubit. And these transmont qubits can be detected very efficiently. These are data from our lab. I don't really have time to explain the principle of the measurement, but it is based on cavity QED principle. It's based on the coupling of this qubit to a resonator. And these are the basics actually date back to all the cavity QED work by Serge Haroche group in particular, and all the new developments that have been transferred to superconducting circuits when they are coupled, qubits coupled to resonators. So this physics is the same, and it is used to actually perform a single-shot measurement of the qubit state by just sending microwaves, and you see that we have good discrimination between the two states. Right? This is what matters for this experiment. So based on this, how are we going to do this single photon counting? And here again, this is the scheme that was developed by Zaki and Emmanuel. And so the starting point is that imagine you have this two-level system. So now this Bloch sphere represents the qubit state. And so the most naive way that you could think of measuring photons would be to enclose this qubit in a cavity and have incoming photons, right? And then if the photon is at resonance with the qubit will be excited. So that sounds like a good idea. It's not so good because basically the reverse process is also possible. The qubit can be de-excited and re-emit the photon. So this idea is a bit limited in its, and so we need a better idea. And so the better idea comes by coupling the qubit not only to one cavity, where the input photon will come, but to a second cavity also, at frequency omega b, at a different frequency. So we have three frequencies, have omega A, omega b, omega q. And so, okay, but now what do you do? And in parallel, you pump the qubit with a fourth frequency, omega p. And you do so that there is this resonance condition that is satisfied. We can tune the pump frequency to satisfy this resonance condition. So what does it lead to? It means that now, if we have a photon that arrives, a photon is omega A, a pump photon can be absorbed, leading to an excitation of the qubit and the emission of a photon in the other mode, omega b. So, okay, that's fine. That's called four-wave mixing, right? This is not new. But that's not enough also because we still are left with a unitary process, right? If we keep doing that, the photon will again come back into the measurement line at omega A. So here the idea is that now we can also introduce dissipation in the second mode. And if we let the photons now go away from the mode B, then this is good because then the reverse process is no longer possible since the photon has vanished. Right? So this is, by dissipation engineering, we keep an effective Hamiltonian interaction, which is an effective interaction which consists in absorbing a photon in the input mode and exciting the qubit. And that's it. Right? And that's irreversible. And that's good because then we can measure the qubit very quietly and we have all the time in the world to do that. So there is a nice thing in this. This is a nice principle, but there is an even also a nice thing that, in fact, this detector can be reset. There is a built-in reset because now imagine that we have. We are sending now. Imagine we are sending some photons on the B mode and without any photon in the A mode. Then it's the reverse process that's going to be triggered, and this will relax actively the qubit. This is a nice feature because qubits can be long-lived, and so it's nice to bring them actively back in the ground state because when they are in the excited state, you cannot measure, right? So it just makes the detector more efficient. All right, so now these were all concepts, but the real chip looks like this. the qubit is this, you see the capacitor of the qubit. It's coupled to an input resonator, so the photons will be arriving from this left node, entering the input resonator. It's actually made tunable with a squid because we need to tune the frequency of the detector to the frequency of the spins that we are interested, right? So this is the detector resonator. And there is this output second mode that is shown here in green, and the pump line in purple. Right. And so then the detector operation is, corresponds to cycles of really microwave pulses. So here, remember that the orange is the so now we are going to test if this detector works. And for that, we are going to send a little bit of signal on the detection mode. In parallel, we pump on the qubit. And then, so this is a detection window. It's 4 microseconds long. Then we stop the detection. We detect the qubit. This is the detection phase. And then we reset it by sending photons on the other port without having anything on the... And this is a cycle. So, and then we repeat. And these are traces that we see. So look, this cycle takes 10 microseconds, and now we are looking at 25 milliseconds time trace. This means we have repeated this cycle a few thousand times. And when we are not sending any photons, this is what we see. We see mostly no clicks and a few clicks. This is really looking like an optical photodetector curve. And then when we send a bit of signal on the orange ports, there are no spins. Huh? This is just to test the detector first. We see that we have more clicks and more clicks and more clicks. So we have some, it seems to be working as a photodetector. In fact, so this is really, the trace in this off state is really the dark count rate. And in this measurement, the dark count rate is 0.4 per millisecond, compared to a cycle time of 10 microseconds. So really, in more than 99% of the cases, there is no photon detected when no photon is present. So it's not so bad. The total efficiency we calibrate also, that's including the duty cycle, and it's 20%, which is also not so bad compared to optical detectors. So now let's use it to detect spins. And so we are combining, we have this first, this spin device. We have, again, the resonator with the spins below. Here in this experiment, we are using bismuth donors, again, in isotopically enriched silicon. The resonator frequency is at 6.9 gigahertz, you see. So we have to apply some maybe 17 millitesla field to bring the two systems in resonance. And then we have a coaxial cable and another device with this single microwave photon counter. You recognize here the qubit in the middle. This is the input resonator, which is tunable, and this is the output resonator. And this is to show you that the detector is indeed tunable, and we can, by applying a flux in the squid loop, we can bring it in resonance with the spin resonator. And this is, again, the detection cycle that is repeated. So what does it give? So now the experiment consists in just exciting the spins with a pipe pulse and counting the photons with the photodetector. And this is an example of a time trace. This is a single time trace. You see that now we are measuring on the time scale of 1 second after the pipe pulse. And you see that, OK, we have many clicks, but you can see even by the bare eye that there are more clicks at the beginning, in the first 100 milliseconds, than at the end of the time trace. And so we can repeat this sequence many times. We can make histograms and then, therefore, measure the number of counts per second as a function of the waiting time since the pipe pulse. And this is the curve that we get. So in blue is the curve when we don't apply a pipe pulse. It is, of course, flat because there is nothing at time t equals 0 happening. This is the dark count level. But when we apply a pipe pulse, we see that there is an excess of photons detected that decays over a time scale of a few hundred milliseconds back to the dark count level. So this looks like exactly what we wanted to detect. Is this really the spin fluorescence? Well, to answer this question, it's actually interesting to compare this curve of excess photons detected to the curve of spin relaxation that we can measure independently. So we can measure in the same experiment, in the same cooldown, we can also measure how do the spins relax. And we see that they relax exactly in 300 milliseconds. And when we fit this excess photon count, we find also 300 milliseconds. So the correspondence between these two numbers is a direct proof that we are indeed here detecting the fluorescence photons emitted by the spins with a photon counter. So just a small remark that, in fact, there is a little excess of noise at the beginning, excess of counts, and we have very good evidence that this is due to a different phenomenon. This is not due to the spins in our experiment. This is due to charged two-level systems impurities that are relaxing radiatively at the beginning of our experiment. So this is a detail, and I won't spend time on it. So if this is the spin signal, we should be able to do some spin coherent manipulation, and this is what we do here. Now, you see what we do is we integrate the excess number of counts in this curve, and we change the time of pulse, of excitation pulse. So this curve corresponds to a certain time for a pi pulse, but now we can vary this time. And we see that the excess number of photons is indeed oscillating. And when we plot the oscillation frequency and we change the amplitude of the driving tone, it is linear. So these are indeed Rabi oscillations. And this decay is not due to decoherence, it's due to the spread of Rabi frequency in the device, and we understand it also quantitatively. So this is a proof that indeed we can also detect Rabi oscillations by fluorescence. And but finally, so fluorescence is nice, but we have our photon counter. Why not detecting also an echo? And this also works, of course. So we can apply our spin echo sequence, so pi over 2 pi pulse, and then we are expecting some emission time tau afterwards. And here you see these are remnants of the driving pulses indicating the time. So this is the time at which the echo is expected, and indeed we see an excess of counts. So these are curves in which we have accumulated many counts, because otherwise there is just one click at most. But you see that indeed we have an excess of counts at the time of the echo. So this is, in a sense, the first echo detection by a microwave photon counter. This is the analogous of photon echoes in optics, right? And we can also verify that when we change the duration of the refocusing pulse, we observe Rabi oscillations. And we can also do spin spectroscopy. And now we have 3 ways of measuring the spins. We can measure them by our own old spin echo technique combined with field detection. That's one of these 3 curves. I forgot which one. We can detect them by fluorescence, and we can detect them by echo, photon echo, and they all give the same spin resonance line. So this is a clear proof that we are indeed detecting the spins, the bismuth spins in this way. So now, so this is to demonstrate this photon detection, this spin detection by photon counting. Now there is an interesting thing, which is to discuss a bit the performance of these detection methods. And for that, we need to go to statistics and to look a little bit at each detection method. So here in this slide, I want to compare echo detection and fluorescence detection. And so here, this is again an echo curve. This is the echo. And you see that the mean photon number detected, so the echo is very short, right? It's a few microseconds. So in essence, if we had more than 1 photon, we would not detect it because the detector would saturate. But it turns out that in our experiment, indeed, the number of photons detected is on the average of 0.3, right? So this is bar. So here you see that we have here a histogram showing the probability of finding a photon outside of the echo and at the echo. Outside of the echo is the blue curve. You see that in most cases we see no photons. This is just the dark count contribution. And then in the orange case, this is the echo, we have much more chances to find a photon. And this is what this big bin here indicates. And so this is for the echo detection. And we can do also a statistical analysis for the fluorescence detection. And here, this is now by integrating the number of counts on some detection windows. So you see this is indicated. This is of order T1, obviously. So we are just integrating the number of counts on the T1 window. And we are plotting them then as a histogram by repeating each sequence and plotting them as a histogram without pi pulse. This is the blue curve. And with pi pulse, this is the purple curve. Here again, this graph is averaged, right? But here we keep the statistics. And so, yes. So again, there is a very big difference just in time scales between these two signals, right? We have to realize that the echo detection the echo lasts 3 microseconds, and the fluorescence is for 500 milliseconds. It's really during this T1 time of relaxation. Now, what is the level of this signal? We are speaking of sensitivity, signal to noise. So how much is the signal? In echo detection, we have a signal which is this difference here, and you see that it's approximately 0.3 photons on average. So the echo size is 0.3 photons. Now, in fluorescence, and this is related to, of course, the echo size is just the squared of this echo amplitude that we've used previously, and in this case, this is. And note that here, interestingly, the echo, when it's photodetected, is proportional to n squared, so to the number of spins squared. This is an evidence that echo emission is a super radiant phenomenon because it's phase coherent, right? So the amplitude of the field is proportional to n, but the energy is proportional to n squared. On the other hand, fluorescence is incoherent emission. It is proportional to n. So it's very simple. We have n photons emitting. So what we expect is just to detect n photons times some global efficiency, which is how many photons we lose in the lines, etc. So it's just eta n. And you see that in our case, what is this average photon number? Well, it's the difference between the average of the two histograms, and that's 150. So there is much more photons in the fluorescence than in the echo. This is not really a surprise. The echo is by essence a very weak phenomenon. It's super radiant, but it occurs very fast. And so by essence, it has less energy than spin relaxation. So how about the noise? That's the signal. The noise here, this photon is emitted. Echo is a coherent state, so the noise is the square root of the photon number, right? And in this case, this is 0.5, and this is limited by shot noise. In the case of fluorescence, what is the noise? Well, the noise is here the square root of has two contributions. The noise in the fluorescence case. One contribution comes from the dark counts. This is alpha is the dark count rate. We are integrating during a time T1. So we have, on average, alpha T1 dark counts. But there is noise associated to this detection because this is a stochastic process. And therefore, this is the square root of this quantity which plays a role. So that's the dark count contribution. There is also a contribution due to the fact that n photons are emitted, but they are detected with an efficiency eta. And so if eta is not 1, not all the photons can reach, and there is noise associated to this stochasticity also. So the noise is then square root of alpha T1 is the sum of two contributions, dark count noise and bad detection efficiency noise. Now, in our case, you see that the dark count is by far dominating, because this is visible here. Dark count level is 900, whereas the signal level is 150. So we are dominated by the dark count contribution, and so the square root of 900 is 30, and you see that here we have 30. So this is really dark count limited. So where are we? Then signal to noise in the echo detection is 0.6, and the fluorescence detection is 5. So we already have 10 times higher signal to noise ratio, whereas here we are limited by dark counts that could be reduced much further if we had a better detector. So this shows, for us, this is a strong indication that this method of fluorescence detection has a very high potential. In fact, we are already above the usual echo detection signal to noise. And so in the future, the path towards future experiments is very clear. We would like to have a lower dark count rate, to have a better detector. We would like to reduce the dark count rate and also a higher efficiency. And in parallel, we also like the spins to decay faster because you see that the noise here is proportional to T1. So if we reduce T1, we will also have less noise. So this is the direction that we are now taking. And so with that, I would like to conclude. First point is that I hope to have convinced you that superconducting circuits enable unprecedented sensitivity for the usual inductive detection of ESR spectroscopy. Entering the few spins, we can detect typically 100 spins. Squeezing can help a bit, but squeezing is always difficult to use as a very powerful method. We have, by being able to measure ESR spectroscopy at millikelvin, we can obtain very long coherence times in different systems, different spin systems, approaching the second, and this can have interesting applications in quantum information processing that we are trying to explore also. And finally, we have this new detection method that is enabled by the Purcell effect and the development of microwave photon counters by photon counting of the spin fluorescence. And we believe this will be very well suited for few spin detection, and the path is very clear in the future that we would like to use this method with new developments, improvements of the photon counter and also of the spin devices to develop real practical single spin ESR spectroscopy, which we believe is really within reach. And with that, I would like to conclude. So I would like to acknowledge the present members of this spin project, and in particular, so in the data that I presented, I would like to emphasize in particular Marianne Ledantec and Emanuele Albertinale, and Miloš Rancic as a postdoc who contributed to this data most, and my colleague Emmanuel Furin, especially for the development of the microwave photodetector, and in the former members, Vishal Ranjan, former postdoc in our group, who also contributed to what I presented. And with that, I will thank you for your attention.